Hello, we are Team A10, and this is our Reflow Oven Controller for ELEC 291. Using two circuits, a K-type thermocouple, assembly code, Python, and a solid-state relay box, we were able to regulate temperature and automate the reflow soldering process using a toaster oven. Our design followed this box diagram. In this part of the video, we will walk you through the different sections and how they're tied together. Before starting the reflow oven process, we can manually set the timing that we want each state of our oven to follow. Our team has also included an additional feature. By pressing any one of the last two buttons on the right, you can access Set Presets. The first button sets all of the state times to 0, and the other button follows the times given by our professor, Jesus. In the case that the user starts the process but then changes their mind and wants to abort it, they can press the manual reset button, which turns off the oven and displays a custom LCD screen. To demonstrate the whole process of our oven, we will follow through with the preset times given by our professor. Pressing the leftmost button starts the procedure and puts us into state 1 of the reflow state finite state machine. In our example, once the temperature inside the oven goes above 150 degrees, we will enter state 2. As we go through the different reflow states in our oven, we are able to monitor the real-time progress using our custom-made Python graphical user interface, which we designed using tkinter to resemble an oven. At the top right, you can see our status indicator, which tells us when the reflow process is off, in progress, cooling, or complete. Right below that, we have our rotating dial, which indicates what state we are currently in, for which we created the visuals. Both of these features update synchronously based on the data being sent from the microcontroller to Python using PuTTY. As our system enters the cooling state, you will see our main feature in action, a servo-operated oven opener that assists with cooling. With our oven finishing its baking process, we now have the complete graph displayed on the left. Our graph has the added feature of having a hover function that displays the time, temperature, and range of temperatures considered in the point. Another graph feature is that by pressing the middle button, you can change the graph from Celsius to Fahrenheit, which also changes the axes and the color. When pressing the left button, you can boot up the stage information page, which displays the starting times of each stage. This page is also updated automatically. We also have another page that displays our group photo and team name. Finally, when clicking the rightmost button, you are able to boot up the export page, where you can export the graph in a variety of options. Here's an example of what it looks like to export the graph as an Excel file. Returning to our servo-operated cooling feature, it's important for you to know how we made this feature function. To control the rotation of the servo motor, we used a 555 timer with pulse width modulation. The blue potentiometer controlled the duty cycle of the PWM signal coming from the 555 timer, and rotating the potentiometer resulted in a corresponding angle of rotation in the servo motor. For servo logic, an NPN transistor in saturation mode was used to control the servo motor. A constant voltage from the microcontroller's pin was applied to the transistor's base while the collector received the PWM signal. Since the microcontroller's current wasn't enough to fully saturate the transistor, its output was passed through two NOT gates before reaching the base. The emitter was connected to the servo's control pin. Using the computer's serial port to supply power to the circuit for the microcontroller and the servo caused issues involving back EMF and insufficient current supply. To solve this, the circuit for controlling the servo motor used a 9-volt battery as an external power supply, and the ground rails for both circuits were connected to ensure a common ground voltage. Since 9 volts is outside the voltage range for the chip used for the NOT gates, a 5-volt voltage regulator was also used. Now, how does this all work? The servo motor is first manually disconnected from power and rotated 180 degrees away from the angle of rotation determined by the PWM signal. Then it is reconnected to power. When the reflow oven reaches its cooling state, the microcontroller outputs a voltage from one of its pins, which is connected to the base of an NPN. This allows the PWM signal from the 555 timer to reach the servo. When the servo receives this signal, it rotates 180 degrees, pulling on a nylon fishing line connected to the handle of the reflow oven, which then opens it. The last feature we programmed into our oven was the required safety feature. As shown in the video currently playing, if our oven does not reach the required temperature of 50 degrees Celsius in the first 60 seconds of operation, the reflow process would be terminated. To ensure the accuracy of our oven, we ran many rounds of data validation to ensure our temperature readings were within 3 degrees of the actual temperature with reference to multimeter readings. In summary, our Reflow Oven Controller successfully automates the reflow soldering process with precise temperature control and real-time monitoring, ensuring both safety and efficiency. With this system, we successfully soldered multiple functional PCBs for future labs, demonstrating the effectiveness of our design. Given more time, we would have implemented additional safety features, conducted further temperature testing, and enhanced UI integration between MATLAB, PuTTY, and tkinter. Thank you for taking the time to learn about our project. We hope you enjoyed our presentation.